Okay, in this tutorial, I'm going to help you answer a range of questions related to the use of a Pearson's product moment correlation coefficient statistical test that you are using to examine or analyze the relationship between two sets of data. Now, the Pearson's product moment correlation coefficient is just more commonly known as the Pearson's statistical test. And it is a test that is used for a number of reasons which we're going to explore. Now, you'll be already have completed task 6, where you're introduced to the idea of what a null hypothesis is, and you will have also read some background information on the use of statistics to analyze data. In this particular case, you will have formulated a null hypothesis, which is an important step prior to conducting a statistical test. And that will have been done, and it will have probably read something like there is no statistical relationship between the level of vehicles, which is the x variable, and the number of pedestrians in an area, which is the y variable. So we are stating for a mathematical point of view that there is no relationship. And that is only done when you're about to then conduct a statistical test. Okay, so that will have outlined task 6 largely. Let's have a little look at actually what we're now doing with that information to test whether that null hypothesis is accurate or not. And we've got a series of questions I want to look at here. And the first one is, with reference to the data above and the 3 possible relationships shown below, what type of relationship do these 2 variables have? And if they do have a relationship, how strong is it? Okay, well, I'm going to look down below here to the possible relationships that you can get from a statistical test. And when you look at a scatter graph, your scatter graph is going to look either like this, this, or this. Now, that is assuming you have what's known as a linear relationship. I'll talk more about that in a second. If we have a look at the scatter graph we have got here from our 10 sites that we visited, in this case in Dundee city centre, then we can see that's then plotted on the scatter. A line of best fit has been added, and it seems to suggest that as one variable increases, in the case of this data set, traffic, which is our x variable, as it increases, so does the pedestrian count, according to the data we've gathered here. So if we compare that down here, that would be what we call a positive correlation. Now, if most of them, of the data points, are relatively near to our line of best fit, and there is a very limited number of outliers or anomalies, and that would be a piece of data down here or up here, then we would be probably suggesting we have a reasonably strong statistical relationship, because our scatter graph looks something like that. So we have a fairly strong positive correlation. We cannot say we have a perfect correlation. To have a perfect correlation, you have to have every number, as every number gets higher, so would its paired number. So in this case, our lowest, which is 40, would also have to be our lowest pedestrian count of 35, but that's not the case. We have a traffic count of 45, which actually has a lower pedestrian count. So we don't have a perfect correlation, but we do seem to be getting a strong indication that there's a strong positive correlation. Now, if we have a look at the question, it says, with reference to the data above and the 3 possible relationships shown, what type of relationship do these variables have? Now, before we leave this, one final thing, how strong is it? It's likely to have a strength of quite close to 1. I'm just going to talk a little bit more about what that 1 means. When we do our test in a second, we are going to get a result that ranges somewhere between -1 and +1. And that's the only range of results we can get from the test we're about to do. A +1 result is a perfect positive relationship, which is where every value as you go along the x-axis is higher than along the y. And that, if we had that, then that would be 1, +1. If it was the opposite, that as 1 increases, it automatically decreases and it's always by the same amount, that would be a perfect negative correlation. That would be -1. And if our data looked like this, it's very likely our result would be 0. So our scatter graph suggests that our result is likely to be close to +1. And when we do the test in a second, you'll see whether it is or isn't. Okay, so that is question 1. I would now pause, replay any of this you need to answer this particular question. And let's go on to question 2. Why is this test a suitable test for the data you have gathered and the aim that the students have? Okay, now you read page 48 and 49 of the Advanced Higher Geography textbook, and that does outline the purpose of doing these tests. Why they're suited, why would you be choosing this test? And we have 2 data sets, and the students want to find out, investigate whether the number of vehicles in location influences the number of pedestrians. And when we look at the scatter graph, we seem to have a suggestion that yes, it does. It seems to suggest that as the traffic count increases, the pedestrian count increases. And we could even give an example. So for example, when the traffic count was low at location 4 there, the pedestrian count was very low at 35. When the traffic count was very high at 120 at location 5 in our city centre, the pedestrian count was very high at 180. So that evidence from the table and the scatter graph seems to suggest a strong relationship. Okay, that's fine. We could just use a scatter graph, but why use this statistical test? Well, because the statistical test is going to give us a result which is going to tell us how significant that relationship is. Just how strong is it? How sure can we be that this was not just a random event, set of results, and actually we don't have a relationship? And that's where statistical tests come in. They tell us the level of significance of our results. And that gives us a stronger way of either accepting or rejecting a hypothesis when we get to our conclusions. So the first purpose for doing it is where we are aiming to prove whether there is a statistical relationship between 2 pieces of data. Now, the next reason for doing this test is that our data is, in this case, what we call interval data. So what we mean by that is it's numbers. We have counted. At location 1, we had 45 vehicles and we had 23 pedestrians. And our numbers start at 0. Because you can't have a negative number of cars or pedestrians. And when we have numbers that start at 0 and go up the way, we call that interval data. And because both of our data sets, our traffic count and our pedestrian count, are interval data, we are also able to do this particular statistical test to see if there is a relationship. Now, the third reason, and you should be recording all of these down, I'm just going to show you another reason why we can go ahead and do this. So let me just have a look at this sheet here. Okay, the reason we can is this was our results. We have what we call a linear relationship between our 2 variables. And what that means is as one increases, the other increases at a proportional rate. Okay, now to really explain that to you, what we mean by a linear relationship is to show you what a non-linear relationship looks like. Now, what we can see here is that as traffic increases up to the variables about 20 cars, there is very, very slow increase in pedestrians. But when we get above 20, as we go up every 5 vehicles, the number of pedestrians increases dramatically. In the case up at the upper end by at least 50 for every jump in 5 pedestrians. Okay, and that's what we call a non-linear relationship. And if this was the relationship between our 2 pieces of data, then we wouldn't be able to do a Pearson's. So we conduct a scatter graph first to determine whether there is a linear relationship or not. And if we determine that there is a linear relationship, then we can go ahead and do it. Another factor that allows us to do this particular test and why it's useful is because we have no outliers, or what we also call anomalies. If we had some anomalies, some pieces of data over here or down here, now these would be outliers. These would be values that are far away from the trend line, and it would mean that it's not really suitable to do a Pearson's test. And finally, another reason that we can do it is we actually have whilst not a very large data set, we have above the recognized minimum. It's generally recognized that if you have 5 or less than 5 pairs of data, and this is a pair right here, if we had only 4, we'd only been to 4 locations, then we really should not be doing a Pearson statistical test. But as we have 5 or more pairs of data, we can go ahead and do that. Right, you might want to pause it now because we've done a lot of reasons about why we can go ahead and do this test. Okay. Now, the third question, based on the result of the Pearson test, what does the result mean? Now, we haven't yet seen what our result is. So let me go through how you yourself could do this test using Google Sheets. In future, you might very well choose to test 2 pieces of data you've gathered and use this method to find out what your result means. So if we go to our spreadsheet, we can see that we have over here a place we want to put our result. I've just created that for us to place our result. And what I want to do is find out whether there is a relationship between my 2 variables. Now, there is a mathematical way of doing this where you have to have a calculator and go through quite a lengthy process using a formula to do that. However, many spreadsheets do lots of different statistical testing. And Pearson's test happens to be one that Google Sheets do. So click in the cell where we want to get our result. And let's go and find it. So we click on this little button up here and we go to all. And if we scroll down the all to the letter P, we will get to a test called Pearson, which we will see right there. Now we select it. Now the first thing it's going to do is it's going to want my 2 data sets. And I'm going to have to now highlight them. So I'll have created my spreadsheet over here. I've got my data all lined up. I've got my traffic in one column and I've got my pedestrian in the other column. I don't need to highlight these. These are just words. I want to highlight my pairs of data. So I'm going to drag across my 2 columns of data. And you can see it's highlighted B2 to C11. Okay, so that's cell B2 all the way down to C11. And that is my data set. I'm going to hit the enter button on my keyboard and it's told me it's not available. Let me just try that again. That's data set number 1. We are going to get there, so just bear with me 1 second. Okay, you have to apologize with me for listening and me getting it slightly wrong. Let me just do that one more time. I'm going to show you how to do this as I talk to you. And of course, you might want to play back this part of the tutorial in future when you're doing your own Pearson's test. So I've gone and selected it from up here. It says equals Pearson in capitals bracket. I'm now going to select my first column and I'm going to hold down on my keyboard the CTRL button, which is the butterfly button if you're a MacBook user. Holding that button down, I then can select a second column of data, and you'll see it's B2 to B11, comma C2 to C11. And now I'm going to hit enter, and I have a result 0.847. So the first thing we need to do is go back here and look at, based on the result, what does the result mean? Well, we would first say our result is, and tell me what the result is. It's 0.847. Now, if you remember what I was saying about this result is quite close to the number 1, but it's not number 1, but it is a positive number. There's not a negative number there. So I would say this is suggests a positive relationship. The final thing you'd want to say is because this number is quite close to 1, it suggests a strong positive relationship. Now, at the moment, that is all you can do with this number. There's nothing more you can say about 0.847. To get to the final step, we need to look at what does this result actually mean? Is it significant? And I'm going to show you how to find that out in a second, and you're going to use my ideas to complete this. This is a way of writing up a statistical test. It's one used by all mathematicians and humanities and scientists when they report statistical results. Now you can do the first bit already. The result of, and in this case, 0.847 suggests a positive relationship between the 2 data sets, which means as one number gets higher, the other gets higher, of course. This result was, now this is where we need to see what our result means. This is where you need to understand something about tables of significance. Now, this is a critical values for Pearson's table of significance. You can look these up online. And this is specifically for the Pearson's test. And the first thing you have to do is find out what your DF is before we can even look at these numbers and understand what they mean. Now, the DF, or what's known as the degrees of freedom, is calculated by knowing the number of pairs you've got minus 1. Now, we've got 10 pairs. This is the 10 pairs here. So it's 10 minus 1. So the degrees of freedom would be 9. So we're going to be working on this line of data. Okay. Now, in order to interpret what this line of data means, we need to first of all find out if this result is higher than any of these results. Well, as a matter of fact, this result of 0.847 is higher than every single one of these results, especially this one down here, 0.735 or 0.735. Now, what does that actually mean? Well, it means if it's higher than this, then we have a level of significance that is higher than 0.01. Okay, so our result is better than the 0.01 level for 9 degrees of freedom. Okay, so let's go and have a look at what's that all going to mean for typing this. So this result was, now it was higher than the, now what was the critical value? Than the 0.735. So that's what we typed there, critical value for, now what was the degrees of freedom? Go back to your table, 0.01 degrees of freedom. So that's what you put there, 0.01 degrees of freedom, meaning that the result is significant to her. Now, this is the complex bit. Well, most people don't understand that. If your result does get higher than this, it means that you are 99% sure that you have a relationship. Okay. If your result got higher than this, it would be 98% sure. This one is 95% sure. And if it got higher than this, so you'd have needed a 0.521, you'd have been 90% sure. So you are 99%. There's a 99% of confidence that we therefore, and in this case, because we are higher, we get to reject the null hypothesis. Remember, the null hypothesis was that there was no relationship between traffic and pedestrians. But we're going to reject that. We're going to bin it. So we write we reject. And when we reject the null, we get to accept the alternate, which that as one gets higher, traffic, pedestrians gets higher. Okay. So what have we discovered looking at this data? Well, we are now 99% sure that as the traffic volume increases, the pedestrian increases. Okay, that's a lot better than just saying the scatter graph suggests there is a relationship. We are now actually gone as far as saying we're 99% sure. I would strongly recommend that you use this test if you have interval data. Let's have a look at the final question. Discuss the strengths and weaknesses of using statistical tests to analyze data. You can write up your answer for this. Pause the video though now to just make sure question 4 has been finished. Right, let's have a quick think about question 5. Assuming you've answered all the other ones. So why use this test and what are some of its limitations? Okay, so I think we've kind of explored its strengths already to an extent. So the strengths are it works really well when you have a linear data set, which means that as the values as the x value gets higher by a certain amount, the y gets increases also by that amount. And it's also good for data sets where there aren't any or very few outliers, which would affect the data set widely. One other thing you can say is that it's perfect for this. So there's 2 reasons, because you're trying to find out whether there is a relationship. So it is a test that's suited to finding a relationship between 2 variables. And because we have interval data, remember that was just where you've counted the data starting at 0 and it's gone up from 0, we can also conduct this test. So it's those factors that are make it strong? What are its weaknesses or its limitations? Okay, so its limitations are, first of all, it only really works with data sets that are large. You can use it for data sets which have 5 or more, but it's not recommended. And we have a data set of 10, and therefore, even though we're 99% sure, it's a very small data set, and therefore there's a strong chance that this was just a random association. Had we visited 20 locations across Dundee, we may not have found such a strong or any relationship at all. So small data sets are its limitation. Of course, you also have to have very few outliers, because outliers really affect the Pearson test, and it only works with linear um, data. One other big criticism that it gets is that if you were to conduct this using the mathematical formula, it is very tedious and time consuming to do, and it requires a high degree of mathematical skill, which is often beyond most, certainly high school students, but even to an extent people studying at university. So it's a difficult test to interpret as well, which would be another criticism of the Pearson test. Okay, so use those ideas and write them up in as much detail as you can as bullet points here, so you've got a really good answer for what the strengths or weaknesses of using this test are, because that is a very common exam question.